delighted to welcome Professor Choon from NUS, who is going to give us the keynote on a topic that is very close to my own heart. And we were just discussing how programmable networks and the continued work in that area is so important. And we're going to be hearing from Professor Chan about his latest work. Professor Chan is extremely well known, so I don't think he needs an introduction. He's been at NUS for several years, working on a variety of topics, and including 5G and 6G networks more recently. He has many best paper awards and other awards to his credit. It'll take a long time to go through all of them. He's currently also, in addition to being a professor, he's also the vice dean for graduate affairs. And we're really delighted to have him here. We'll take some questions at the end. So hold your questions if you can, unless you want to have people asking questions in the middle of your talk.
It's
we can wait.
Yeah.
We can. So without further ado, please join me in welcoming Professor Chan to give the keynote address.
Yeah, hi, good morning. So first of all, again, I express my thanks to the organizer of the APNet for inviting me today to be here to give this talk and to share some of this work that I have been doing. So this topic is kind of a special place in my heart because way back when I was a grad student in 1990s, my advisor was always very much intrigued by the idea of programmable networks. So he has been pushing us to look at this topic. And I must say, kind of is interesting to see how the field evolves over all this, this era. Everyone. Can you use the mouse? Mouse. No, this is one. All right, so just a quick kind of a background. So I guess even up to now, right? If you look at a network hardware, it's very much closed systems, and it's a classic, but we are still living in that era. But you buy a network switch, very often there's very little you can make changes to it. It comes to all the functionality, built in, and it's really hard to make changes. We have been trying to make all these things open source and everything, but it's not so easy to fight against the commercial interests. Because I say legacy, when I think of it, legacy as in how things tends to be. You have a fixed pipeline of network processing engines. We call it that when the packet comes in, you have the way to pass it. It goes through some processing, and then the packet leaves a number, right? So this part of it is very much fixed. You can't really do much to it. And on top of it, because you have a interface, again, this is more or less static. The ASIC is not available to you. And then you have a set of APIs, Cisco called it CLI, right? Command line interfaces that you can write. But things are more or less the way it is. It's very hard to make changes. So we have been trying to, this is all very well. Can I use the keyboard instead? Yes, easier to just use this one. Yeah, this no. Okay, now it's okay. I use the keyboard. All right. Yeah. All right. So we've been trying. Since at least when I was a grad student in the 1990s, we were intrigued that in that era, we think about making the network more programmable. At least some of the concepts already being shared. You basically first of all you want to control plane, but you can write code in RAMs, and you have a separation between the hardware and software, the control and the data plane, and then you have a standardized set of APIs that you can write on the control plane that controls how the data plane works, right? So this is at least the way we think about network that's programmable, and it's more or less very close to what we think of the open flow or the SDN era, right? But one big problem in those eras is that there's no hardware, right? I guess those of us who are working on it, you buy ATM switches and try to think of a way to design a fixed API. So there were quite a bit of effort in certain groups. So we were actually having, at least my research group, we were thinking about pushing these things on the IEEE and then the IETF as your own group. If you remember this thing that the idea about these two is very similar to what OpenFlow does. It's a defined interfaces, but there's no hardware, so things get a bit tricky. And of course, we were kind of in somewhat a state of I like to do something, but we can't make a lot of progress. I think the first kind of breakthrough was when SDN, as in OpenFlow came about, but we finally have a real platform, right? A real platform that you can try, and the underlying structure and hardware is pretty much the same. Okay, you have now the big difference is that you have an open interface for the control plane to write, to make modifications to the configurations of the underlying hardware. That kind of make it, you have now a standardized platform. You can write code and the ideal case that it runs on all the switches, doesn't matter what switches you buy, they expose the same interface, right? And then I guess it was really a big improvement based on what we were having for in the earlier era. So that's kind of the early excitement about SDN software. They find out, okay, you write a code, it controls the entire network. Wow, right? But of course, what SDN, at least in that context, doesn't give you is that you are still writing code that runs on the control plane. You have no impact on how the core network functions actually work. You cannot really go and tweak the behavior on the underlying function, right? So I guess this is where with P4 and PISA, with the Tofino switches, that finally we really, what I thought is that we can have a network that is more or less programmable, right? So the big difference here is that now you can actually directly access the underlying hardware with some constraints, of course. If a model and Tofino adopted a more pipeline-based design because that design make it more deterministic in terms of how the function works. So you have less flexibility, but more deterministic behavior. And on top of it, what is nice is that you don't even have to worry about having a standardized API on the control plane now, because the API exposed is whatever code you write on the data plane. And once you have that, you can just basically now generate the interfaces. It's no more fixed. At least then with OpenFlow, give you a fixed set of interfaces. Now the interfaces is function of what you write, right? You have the runtime, and now you think of it. Now the data plane is programmable, and you compile it. You generate a set of interfaces that fits into your P4 behavior, and now everything is more programmable. You more or less get whatever you want to change in some sense, right? So I think this is where I think more or less what happened the last 10 years. A lot of excitement there. And of course, what are the benefits, right? Finally, it's more or less programmable to the extent that, that makes most of us happy. And a lot of the hardware behavior now becomes a software programmable functions. You can make changes now. And of course, for the researchers, we always say that, now I get more functionalities. What kind of exciting stuff I can do, right? So I guess the next thing is that, can we go back and take a look at a lot of the networking functions that we have been using? Can we redesign it in a better way because we have a new platform? Or are there even new things that you probably couldn't do previously? And now you can actually say, okay, I have a much greater capability. Let's do things in a different way, right? So I guess all these are possible. So basically it maps to what kind of functions, right, you think make sense. I think this is, at least when we start, this is really exciting. We finally have a way to think about how we can do things entirely differently and not relying on the hardware vendor to give you a set of instructions that you have to program. You have a lot more control. But again, this is where I'm going to share with you some of the work that we have done. All right, so I'm going to talk about three types of kind of work that I have done in the last, the last 7 to 8 years. So when we started, right? I must say initially when I look at P4, I wasn't sure how flexible it was. We were a bit skeptical. I'm like, is it going to be another SDN or whatever, which is great, but not really what I'm looking for. So I'm glad my PhD students were very persuasive. They say, Prof, let's give it a try. This is something new. You shouldn't be skeptical. Let's go ahead and try it. So I have a new platform. We are kind of just trying to learn what we should do, right? So in fact, when I start, I say, let's have something that I think everybody will need, right? So what does everybody need in a network, independent of the application? So I started off with actually just time synchronization. I'll talk a bit more later. So I'll talk about three. So we started looking at the basic network services, which is time sync and in-network recovery. And then the thing I asked myself is that, again, look at something that that is independent of the applications, right? And then we look at network monitoring, right? I talk about some of those. And finally, we have to build some applications, right? Some network control algorithms. So I'll share some of the work we did on load balancing. And the last 1 to 3 years, I have been kind of looking at 5G network as a data center application. So we look at some of the 5G network applications, like how to do routing and hardware acceleration differently, using programmable networks in the 5G context, right? So I'll kind of go through them. All right, so first, time sync. Time sync has been, a lot of applications need time sync, including the data center. So of course there are existing, tools you can use. You can use NTP by the host, exchange messages, and then you agree on the time. But you realize that, you realize that there's a lot of overhead. And one of the reasons is that if you want fairly high resolution time sync, I'm talking about, let's say, microseconds, you realize that the clock drift is about 20 parts per million, which is 20 microseconds per second. This is considered a decent crystal. So let's say 30 is the average. That means that if you want to achieve resolutions of 10 microseconds, you have to synchronize almost every second. It's a very high overhead, right? So NTP is around, but if you want high resolutions, maybe it's a bit expensive. Of course, there's also existing, even back then, existing some tools like PTP, where you could use the NIC card, the network interfaces, to do time sync, to timestamp. That's possible, but the way that the term is defined is that they actually mainly works on the NIC card. If you want a better time sync, it involves the control plane. Once the control plane is involved, when there's congestion, the accuracy tends to drift. And we're looking at very high accuracy, time sync. So it's very clear. I have a P4 switch now, right? It should be obvious that you can do better time sync because you can program every single stages. So when I started, I actually told my student, this is like a trivial problem. You probably can get a poster done. Okay, but it works out to be a lot harder because there's actually not a single clock on the P4 switches. There are multiple clocks, and they are related in some a specific way. Plus, you think of hardware, at least initially you think of hardware, everything has to be deterministic, right? It should take the same amount of time to go through all the stages. So offsets are easy to compensate for. It's not true. Even the hardware, you're talking about nanoseconds level, the stages do differ depending on the exact payload you have. So different payload will have slightly different processing time in the hardware on the orders of tens of microseconds, right? Because your clock is 1 gigahertz. So all these things actually make the problem a lot harder. So this was shown on the first long paper we published on SOSR. I think it was the best paper that year 2019 because it's easy logically, much harder to do it in practice, right? And I guess we did it. And one of the good things is that by doing this, we actually learn what are the constraints. Like, logically things work like this, but there are a lot of practical constraints that we kind of pick up that, oh, no, this is actually one is a bit easier to implement on the hardware. Sounds more logical, but a bit harder, right? So we kind of learn by actually doing this. So this is kind of, I'm not going to show the results, I'm going to show that, you can actually go to the level of tens of nanoseconds time sync, right? Of course, as you go further away, if the switches are 4 hops away, your accuracy drops. But overall, this is, I guess, on average, you get a fairly good time sync. So we actually open source the code. I think there were some groups that were actually using it in the test, but equally, eating. She was using some of our code to do some of the work for her optical stuff. Right. So okay, so after that, we move on. And I guess one of the things you work on is that besides being interesting, I need students who are very excited about the problem. So they came to me and say, Prof, let's look at link failure, right? I said, why link failure? Because link failure is that when there's a problem in the network, you should fix it in the network, right? Because usually you think of so if something fails, okay, first some mechanism will detect the failure, right? And it takes some time because even if the link fails, talking about hundreds of nanoseconds or few microseconds, it takes time to detect. You cannot just assume that things go bad. You need to wait for a while, right? To detect it. And then, of course, once you know that there's a link failure, you want to change the route, right? Change the route and you choose another route. And then after that, you have to recover, right? And of course, if the switch is not involved, the recovery can only be done end to end. Once you've done end to end, it is a lot slower, right? You introduce a lot of long latency, you can go to timeout, right? So again, once you have packet loss in the network and you deal at the end host, you naturally will have a lot longer delay, and that leads to, and if a lot of short flows, a much longer flow completion time. So we say, well, the rest, detection is a bit hardware. Choosing another route is routing, they're all interesting. But what we can do in the network is you can do local recovery, right? So we call it, in-network packet loss. So again, how do you do in-network packet loss? Because that requires amount of caching, buffering, and timing management and retransmission. And normally the switches don't do that, right? You always do it end-to-end on the wireline network because the assumption is that there's very little packet loss in the network. It's going to be a small problem. But as you grow higher and higher speed, your data centers requires higher performances. Even a small amount of delay here and there adds up, right? So you said, I can do it in the network, why not? In fact, this is usually done, not usually, more commonly done in the wireless network because they have much higher loss. So kind of the underlying techniques is known to us because it's done in the wireless, right? But to do it in a wired network with high speed is also common. I guess it's like, how do you cache a packet? There's no caching, at least in the beginning, right? And this is not like data caching, do lookups. You are caching packets that you have just sent, right? So I guess one can argue that if you can do it, this is the right place because you hide the loss from the endpoint and the recovery is much faster, right? All right, so kind of your goal is to mask the effect of the packet loss for the endpoint, do local recovery. And it was still early. I think if you propose this idea now, people will complain. But back then, it says that you can actually cache the packet by using a loopback. If you loop the packet back within the switch, and then you just have to cache. You do the caching by packet, by doing packet circulation, and you only need to cache enough to handle the time it takes to detect the loss and configure a new route. This is the time. It's not very long, and you don't have to do it for every single route. You do it for the routes that you think are very important, or routes that you think are more prone to loss, right? So if you are more selective and your time of caching is rather short because it's the time it takes for your packet to reach the next switch. So it's one hop. So it's much shorter. All right, so roughly, you have the switch data plane, then you have a buffer and queuing engine. So the challenge is that the default, queue is FIFO, and there's even on the P4 or Tufino, there's not a lot you can change on it. You have later on Tufino 2, you have some priority queues. So you don't have the right queuing discipline, right? So as I mentioned, I jump ahead. So you actually cannot use the routing algorithm. Your goal is the way we did it in SQR is that if you want to protect this particular link, you loop the packet back. So you do consume some bandwidth, right? And because of that, actually there are a couple of challenges. Okay, you keep the recent copies, okay, and you need a timer to know that how old this packet is, and that this packet probably already has reached the other switch because there's no link failure signal coming back, and then you can throw it away, right? And this is actually possible. Even on the earlier, the initial version of Tofino, it already can be done. and this can be done, I think. So what are some of the challenges? Right, first, you need to keep track of how old this packet is, so that you can throw it away when it gets too old, because you need a sense of time. And plus, you cannot just look back on a single pod, because that pod might be very congested. So the way to do it is that you have to distribute this packet circulation onto different pods. Because if you keep looping on the same pod, you actually increase the link utilization. You might introduce packet loss. So you have to share this load. The assumption is that there are sufficient spare capacity on one of the pods, or some of them on the switch. And you use those spare capacity to do this packet circulation. So you have to, again, in runtime, figure out what are the pods that are free, and you do it, right? And then, okay, you can build it. So this actually works quite well. It's one of the elegant earlier work. So SQL looks at link failure, the link fails. So we have a more recent work published 2-3 years now called Link Guardian that handles gray failure. But basically, the link doesn't fail. You just have higher bit error loss than others. And there's a way to kind of do some protection on that link with higher link failure rate. Right? Similar high-level idea, but the details are quite different. Right? I guess I'll go into this. Okay, I guess I'm thinking probably too slow. Okay, next I'll talk about network monitoring. All right, so network monitoring, I guess, if you're familiar with this, one of the core component of network monitoring is sketches, because you can't monitor all the flows. So you need a data structure to kind of do approximation counting. So I guess all going to what is the sketch algorithm and counting sketch. But the idea is that you have a data structure that you can use to track the packet traffic statistics, right? So one of the kind of the limitations of counting sketch is that they tend to use the standard algorithm, use the same memory size for all the flows. But then we know that in many cases, your traffic flow has the elephant and mice thing, like a lot of mice flow, very small flow, and a very small number of elephant flows. So you think about bit efficiency, you need more bits for the elephant because the counts are larger. You actually only need a small number of bits for the mice because they have very small count. But when you start, you do not know, right? So by default, all the counts are the same size. And this is a problem because it means a large number of the flows, you actually underutilize the bits. You have a size that is way too big for the mice, and there are a lot of them. So people are aware of this. So they say that, one of the way to kind of get around this is to so-called separate the mice and the elephant. So for example, one of the paper called Elastic Sketch, they have some structure in front to say, let me know if they will detect the elephant flow first. And then the rest will be mice, right? So that the elephant part, they can use a larger memory, bits per flow, and for mice, it's smaller, right? So this kind of works. The data structure makes sense, but actually non-trivial to put it in the hardware. The key thing is that this should run in the data plane, and to run in the hardware, they kind of work, but they have to make some compromises when they put in the hardware. And then if you run in the hardware, it loses some of the efficiency. So what we did was that, can we revisit this with P4? We know that P4 is a pipeline architecture. Can we design a count mean data structure that is actually more friendly to a pipeline data structure? So what we came up with is like, okay, so the problem is that I need to use different sizes of bits for different flow size, right? But I do not know how big they are at the beginning. So let's think of it this way. At the first level, everybody is small. I use a few bits. And then when they overflow, they are medium size. Then they go to the next level, which I have more bits. And then as they go bigger, they overflow, it will hit the large one, right? So we organize it as from small to big. And the good thing is that every level is actually a pipeline. So think of it, it maps fairly well into how the Tofino pipeline stages work. So the first stage go for the small, next stage go for the bigger ones, and then you keep going. You can have 3 to 4 stages. And this architecture, this structure actually doesn't work very well in software. We do it in software, it's a lot slower because it's less parallelism in software. But in hardware actually works exactly the way the Tofino was designed. So in some sense, we kind of say that, well, we have a data structure that's designed for the hardware. which I thought was interesting. Like we didn't just take a software algorithm and try to squeeze it into the hardware. We started with what makes sense of the hardware and design it, and